temperature. The plate temperature is T0 and the fluid temperature is T infinity. Free steam temperature is T infinity. So what is the rate of convective heat transfer from the hot plate to the fluid? And that we know by Newton's law of cooling, it is equal to Q is equal to convection coefficient H into plate temperature minus free steam temperature. And also, because of the no slip property of the fluid, what will happen? The fluid which is on the wall, that will pass on the heat through conduction only. So if we apply the law of conduction, Fourier's law of heat conduction, we can also find out the heat flux through Fourier's law of heat conduction given by minus conductivity of the fluid K into temperature gradient across the fluid stream given by del T del Y at y equal to 0. So we can also find out the heat flux and also the value of H we can find out provided we know what is the temperature gradient in the y direction at y equal to 0. If we can find out the temperature gradient, we can find out the heat flux, and if we integrate that heat flux over the entire plate, we can get the rate of heat transfer, the total rate of heat transfer over the entire plate. Now to find out the total force, we require to know what is the velocity gradient, and to find out the rate of heat transfer over the entire plate, we require to know what is the temperature gradient. And also to find out the value of H, the convection coefficient, again we require to know what is that heat flux given by minus Kf into del T del Y. Here also we require to know the temperature gradient divided by the temperature difference will give us the value of H. So to find out the force, we require to know the velocity gradient. To find out the heat transfer rate, we require to know the temperature gradient. And also to find out the value of H, we require to know the temperature gradient. So what we understand is that for finding out the basic quantities of force and heat transfer, we require to know how the velocity varies with y, and for this we require to know how the temperature varies with y.
So we are not taking in consideration the K wall, K of the wall, but K of the fluid only.
K of the
Wall.
T of the wall is T0. This is the
Okay.
T0 is the T of the wall minus free steam. T0 minus T infinity.
No, sir. Like we have a kf into dou t dou y at y tending to y positive. Y equals to y positive. So that sense, I'm telling that why we are not matlab, having k wall into dou t dou y.
I can't follow what you are saying. Can you repeat once again?
So why we are not matlab, considering the k of the wall?
T of the wall.
K.
K of the wall. You can take that thing K of the wall, then you have to find out the temperature gradient across the wall.
Mm-hmm.
Okay. What we are doing is that we are finding out the temperature gradient across the fluid. You can
Because
do
that is
that
the
thing.
surface in contact. That's why we are doing it now.
Let me repeat. We can find out this heat transfer. We can find out the heat transfer by taking minus K of the fluid into del T del Y in the fluid region, or minus K of the solid into del T del Y in the solid region. Now, if you require to know either we can take our region of interest here, or we can take our region of interest in the solid domain. Here we have taken it in the fluid domain, and we are trying to find out the temperature gradient in the fluid domain, because we have to find out the temperature gradient. Either way, you have to find out the temperature gradient, either in the fluid domain or in the solid domain. Now, if you want to know the temperature gradient in the solid domain, then you have to know how the temperature varies in the solid domain. And to do that thing, you have to know the value of H in the fluid domain as a boundary condition. You require to know the value of H in the fluid domain.
Okay.
Now, to know that thing, how do we know? We do not know what is the value of H. That is what we are trying to find out in convection heat transfer. This I have already discussed. Let me repeat once again. We can do this in either of the ways. Minus Ks into del T del Y in the Y is equal to 0 minus that is in the downward direction in the solid region. If we want to do that thing, then we have to know how the temperature varies in the solid region. Here we are doing it in the fluid region. Now why we are doing it is that if we want to do this thing, we require to know the boundary condition in the fluid domain. Here the way we are doing, here we require to know what is the boundary condition in the fluid, considering the fluid domain, then what is the boundary condition? Here the boundary condition is at y is equal to 0, we have T is equal to T naught, the temperature of the wall. Whereas if we want to find out the temperature gradient in the solid domain, we have to know what is the boundary condition surrounding the solid. Now in that we have to know the value of H. Now we do not know the value of H. That is what we are trying to find out. That is why if we would have known the value of H, then we could find out simply, if we know the value of H, we can find out the heat transfer rate equal to H into T0 minus T infinity. But the basic question is that we do not know what is the value of H. So we cannot solve the temperature equation in the solid. That is why we cannot find out the del T del Y in the solid domain. That is why we are avoiding the solid domain. We are just taking the solid as a bounding surface where the temperature is known. And what we are trying to concentrate is in the fluid domain, where we are trying to find out the temperature solution, the temperature gradient solution, and taking a boundary condition as T is equal to 0, T0 at Y is equal to 0. Could I clear your question, or you had a different question? I gave you a different answer.
No, sir, you answered it, sir. Okay. That basically we are keen to find out what is the edge, because without getting that we won't be able to solve the K of the solid one. That one I got it, sir.
So we are not going into solution of that. We are avoiding the solution solid part. Now we are looking into the fluid part and trying to solve the fluid part temperature distribution. And once we can do that thing, we can find out the temperature gradient in the fluid part. Then we can find out the value of H. And that is how the heat transfer for fluid flow problems, convection problems, we find out the value of H. Now, to know this thing and also to know this temperature gradient and velocity gradient, we require to know how U varies with xy and how T varies with xy. Once we know these things, how U varies with xy, then only we'll be able to find out del U del Y at Y equal to 0 at each and every x. And then we'll be able to integrate this over the entire stretch of x. Similarly, how T varies with Y and x, if you know, then only we'll be able to find out the heat transfer rate over the entire plate. So our concern will be how to find out the variation of v, the velocity along xyz and time, and how to find out the variation of t along xyz and time. Until unless we can find out how the velocity field is established given by v as a function of xyz and time, and how the temperature field is existing over the fluid domain t as a function of xyz and time, otherwise we will not be able to find out these quantities. So if we want to know these things, it is compulsory upon us that we have to know how the velocity field is distributed over the space and time, and how the temperature is also varying over the space given by xyz and time. Now, so now what we are trying to show you, just a glimpse of what is the form of the equation through solving which we can have the answer how v varies over the xyz and how t varies over xyz. Now, the type of equation that we have to solve to know these answers, how v varies with xyz and t varies with xyz, we have to solve not a unsteady problem we have shown. If it is a steady thing, then what is the kind of equation that we have to solve? If we know the velocity, if you want to find out the velocity of x, velocity over x and y, here what we assume is that along the z direction, that is along the plate depth, the depth of the plate is quite large. So, and we assume that along the depthwise direction, the velocity has no change. Velocity varies only along x and also along y. So that is why we can find out the velocity as a two-dimensional function of xy for a steady state problem. And also temperature, we take it as a two-dimensional problem which is varying along x and y as a steady state problem. So it is not varying along z, also it is not varying along time. So if we want to find out the answer to that, then you have to solve a two-dimensional form of the velocity equation given by the velocity mass conservation equation, that is also known as the continuity equation in two dimension. Now that considering the flow field as a two-dimensional field, we will have a velocity component along x given by u and velocity component along y given by v. U is the velocity component along x and v is the velocity component along y, and both of them they vary along x and y, and there is no three-dimensional flow, there is no velocity component along z which we normally take it as w, that is not there. And also this both of these u and v they do not vary along z, it is invariant along z. So u is a function of x and y, v the velocity component along y is also a function of x and y. Now so we have two unknowns of velocity components given by u and v. U and v are the two velocity components along x and y direction. So there are two unknowns, and to solve for these two unknowns, we have to have one more equation. This is one equation that we can obtain by considering the mass conservation phenomenon. So if you take mass as a conserved quantity, from there you can find out this equation. We'll in fact derive this equation. This is known as the continuity equation, and by taking advantage of the mass conservation property, we can establish this equation, but we require to know one more equation so that we can have two equations for the two unknowns given by u and v. And x and y, they are what? The independent variables. And the dependent variables are the velocity components u and v. Now, so what we do is that only mass conservation equation is not sufficient. We take also help of the momentum conservation equation along x and y. So what we do is that we require to introduce the momentum conservation equation. One is momentum along x given by this form of the equation. I think you have already studied this equation, is known as the one component of the Navier-Stokes equation in your
Yes, sir.
you have come across this thing. Now this is the x direction momentum conservation equation given by u del x plus v del u del y. This is the pressure gradient minus del p del x 1 upon rho, and this is the term that comes due to momentum diffusion. This is known as the convection terms, convective terms, and these are the diffusion term. Just like your heat diffusion, there is a momentum diffusion. X momentum gets diffused along x and y, so it is very similar to your temperature equation. Now, what we see is that the moment we take help of the momentum conservation equation, we are no more confined to two unknowns, u and v. Now, in the process of introducing the momentum equation, we also introduce one more complexity, that is another unknown given by p. So, now that we have three unknowns, u, the velocity component along x, v, the velocity component along y, and also pressure, the pressure is a scalar quantity that varies both along x and y. So now we have three unknowns, and fortunately we have three equations, because there is another momentum conservation equation along y that is very similar. Only thing is that it is like a operator u del del x plus v del del y operating on u. So similar to that, u del del x plus v del del y operating on v, the velocity component. Otherwise, it is similar in form. So it is operating along on u, is operating on v, and here you have the pressure gradient along x. In the second equation, you have the pressure gradient along y, and you have the momentum diffusion along x given by del 2u del x square plus del 2u del y square. You can say del 2 del x square, del 2 del y square of acting on u. Similarly, here also you have del 2 del x square plus del 2 del y square operating on v, the y direction velocity component. So if you solve these three, you can get the knowledge about u, v, and p. And once you have the knowledge about how u varies along x and y, you can find out the velocity gradient along y, del u del y at y equal to 0 at each and every x. So just to get the answer for the force quantity that is exerted on the plate by the fluid, or the force exerted by the plate on the fluid or fluid on the plate, that answer you can get simply by solving the velocity equation given by the mass conservation equation, also called the continuity equation, and the two components of the momentum equation that you can find out. But if you want to know how the temperature varies, then we also have to bring into consideration the energy equation, the energy conservation equation. And so in form is very similar to that u del del x plus v del del y that is acting on t. Here it is the operator u del del x plus v del del y is acting on u. In the second equation it is
স্যার
acting
আপনার
on
ভয়েসটা মনে গ্লিচ করছে, তো আপনি কি একটু
t.
নেটওয়ার্কটা দেখতে পারবেন?
Network university I cannot change. I can have to wait because whenever the train passes, I stay inside the campus very near to the train line. The moment the train goes, it is disturbed. So the moment the train passes away, I think it will be somewhat
আচ্ছা
stabilized.
আচ্ছা, ঠিক আছে।
Now, again, I am starting. The energy equation basically is a conservation of energy equation that introduces the temperature, the scalar quantity temperature, and the form of this energy equation is very identical to the momentum equations. It is also u del del x and v del del y operating on t. And on the right hand side, you have just as you have the momentum diffusion terms, the diffusion terms. Here also you have the thermal diffusion term given by del 2t del x square, del 2t del y square with a multiplier, the thermal diffusivity. You have the multiplier here as the kinematic viscosity or the momentum diffusivity. It's called the momentum diffusivity, and here you have the thermal diffusivity. And if you solve this equation, then you get the knowledge about how T varies along with X and Y, how T varies along X and Y. Now, what you see is that unfortunately, our interest maybe in heat transfer is to know the heat transfer rate that you can obtain by integrating the heat flux, and to know the heat flux you require to know minus kf into del T del Y at Y equal to 0 plus. Now, just to know that thing, we require to know how T varies with X and Y. But as we see, it is not only T that is contained in this equation. This equation also contains unknowns like U, the X velocity component, and the Y direction velocity component V. So even if we are interested only to solve for T, we have to also solve how U varies with X and Y and how V varies with X and Y. Then only you will be able to solve this thing. So whether we like it or not, whether we are interested about the fluid flow field or not, in convection, we have to invariably know how U and V they vary along X and Y, even if we want to know how T varies with X and Y. That is why if we want to know the temperature variation, because it involves U and V, so basically you have to solve for both all these U, V, and T. That is why to solve for temperature, we have to also solve for the velocity equations. So if you want to solve for U and V, then you have to take this all three, because not only U and V will be there, it will be also containing T. So whenever we want to solve a convective flow field, the temperature field, ultimately it will involve in a simultaneous way, in an indirect way, this T will involve U and V. And if you want to solve for U and V, you have to consider these equations, which will ultimately also involve P. So even if we want to solve for a two-dimensional steady-state flow field for temperature, even if you want to know the two-dimensional steady state temperature field, you have to also solve, or you have to also know how is the flow field. By flow field, I mean how U will vary along xy and how V will vary along xy. Because it is U and V that will distort the temperature equation. You see, is the right hand side is very similar to our conduction equation. Because in conduction there is no velocity, so this whole thing becomes 0 and 0. So in conduction you have to solve only the right hand side equal to 0. But because of the presence of the velocity field, what will now happen is that the energy is not only carried away by the diffusion property of the material, but also the energy will be carried away by the convective motion of the flow field. And these are the things that represent the carrying away of the energy by the velocity components U and V. Is the energy carried away due to conduction, the energy carried away due to convection. So in convective flow field, you have to solve for all these four, U, V, P, and T. So there will be four unknowns for a two-dimensional problem, steady state problem. We have four unknowns, U, V, P, and T. And for that, we can take help of all this. And you have to solve them simultaneously. If you want to know temperature, you have to also know simultaneously how U varies with xy, how V varies with xy, and for that, the moment you introduce the velocity, the mass and momentum conservation equation, it also involves P. So ultimately, to solve for T, we have to solve for three more unknowns, U, V, and P. So altogether, this is a case of four unknowns. We have four equation that if we solve, we can ultimately get the solution for U, solution for V, also solution for T.
Acha, sir,
Bolo?
Sir, in these cases, we are considering the fluid is actually moving with some constant velocity, na? It is not accelerating.
It is moving with a constant velocity outside the velocity boundary layer. It is not constant velocity all through. Far away from the plate, it is moving with a constant velocity U infinity. And it is gradually increasing from 0 to y, though at each and every point it is not changing with time. At each and every point it is a steady state that you have considered over here, not changing with time, but there is a variation of U within the velocity boundary layer. U varies from 0 to V, and as a consequence V also will vary in some way. Okay, so U, V, they will vary along x and y, and T also will vary along x and y.
স্যার ইনকম্প্রেসিবল ফ্লুইড নিচ্ছি তো স্যার এখানে
আমি কিছুই বলিনি কি ইনকম্প্রেসেবল নিয়েছি কি কম্প্রেসেবল নিয়েছি, এইখানে দেখে বুঝতে হবে by this thing. Up to this we have not said anything about this thing. Here what we are considering is that we are considering a case that is involving a constant density. If it is not a constant density, then this will not be the form of the mass conservation equation. This is the form of the mass conservation equation when the density is constant. But if the density varies, then it involves another complexity that will show. But in most of the cases, when you solve, you have raised one very interesting point, is that otherwise it is an isothermal flow field, no change in temperature, then the velocity, then the density could have been constant. But the moment we have temperature different at different point, because of difference in temperature, density is going to change at different point, because density is a property that varies with pressure and temperature. Now this, even though temperature is varying, what we do is that we take, otherwise the density does not change much within the region, within the range of temperature that we deal with in convective heat transfer. For most of the cases of heat transfer, we take a very limited range of temperature within which most of the physical phenomena they happen. Suppose it is a hot billet being immersed in a cold, whatever the case, whenever there is a heat transfer, most of the cases we deal with, they deal with cases of range of temperature varying within a limited range. But if your temperature variation is very huge, then we may have to consider the density is changing along with the large change in temperature, because the change in temperature is limited. If you take that thing, then because of the limited change of temperature from T0 to T infinity, whatever the density change, we can ignore that thing, because if we go on taking those things, it will lead to unnecessary complexity without much improvement in accuracy. So we have to make a balance between what is the amount of accuracy that we forego and what is the amount of
Hello?
complexity that we involve.
Okay, sir.
So because engineering is something that has to consider continuously the economic part of anything, any activity that you do. For carrying out any activity involves certain involvement of human activity, which involves certain amount of monetary involvement. So whenever you go
রাত্রি
for a
স্যারের আওয়াজ শুনতে পাচ্ছিস?
হ্যাঁ পাচ্ছি তো শুনতে।
হ্যালো,
হ্যাঁ স্যার শুনতে পাচ্ছি।
না একজন কি পাচ্ছ না নাকি?
কিংসুক মনে হয় পাচ্ছে না, ওই জন্য জিজ্ঞেস করলো।
তাহলে it is your side of the problem. You try to take care of that thing. Now, what I was saying, I forgot what I was saying, is that we are solving a two-dimensional problem, steady state problem, and we consider the density is constant within the region of temperature, range of temperature that we are dealing with. Okay, that is why for a constant density only this equation will be valid. Otherwise, if the density is changing, it will take a more complex form. That will show what is the full form. But fortunately, for most of the cases, we may live with a much more simplified form. Now, this set of equation we can solve. For this, we require to know what are the boundary conditions. And what we do is that at the wall, which is one of the boundary of the fluid is bounded by one side there is a wall that is at y is equal to 0, the wall is existing, and on the wall, what is the velocity component u, that is equal to 0. This is due to a particular characteristics known as the no-slip characteristics of the fluid. Because of that, the velocity is not, the fluid component doesn't have any velocity so long as the wall is a stationary wall. So when the wall is a stationary one, then the velocity of the wall is 0, so is the velocity of the fluid along x. And also, if the plate is a impermeable one, impermeable means there is no perforation and there is no crosswise flow taking place across the plate.
মানে
So
জিরো
if
পেনিট্রেশন।
there is no crosswise flow being injected into the flow field. There may be a plate that is a perforated plate, and through that perforation, either some mass may come out or some mass may be injected into the flow field. That type of thing is we are not considering. We are considering a solid wall, impermeable wall, through across which there is no flow. So V, the velocity component along y, is also equal to 0. And the wall temperature is equal to the fluid temperature, and that is given by T is equal to T0. So that is one side of the boundary condition. In the free stream, what we have is, free stream means that is outside the boundary layer. We have a uniform flow given by U is equal to U infinity, and the V vertical component of velocity is absent because it is a parallel flow that is moving along x, and the temperature is uniform all through, that is given by T is equal to T infinity. Now what we do is that we try to show you the derivation in a very hurried form, because you have already studied, because this derivation also will be required for derivation of the energy equation. That's why we require to discuss everything together. So I'll take a 5 minutes break and then I'll start.
ওকে স্যার।
আচ্ছা, যে শুনতে পাচ্ছ না এখন কি পাচ্ছ?
হ্যাঁ স্যার, হ্যাঁ স্যার, হ্যাঁ স্যার, এখন শুনতে পাচ্ছি।
Sometimes here in my side also, whenever the train goes, I have seen that the thing gets disturbed, but that is the mobile phone gets disturbed. But what I'm using is a university Wi-Fi. I don't know what is happening because that is also not a very healthy Wi-Fi. They are changing this thing.
মিনিস্টার দেখতে গেলে এখন ডিপার্টমেন্টাল লাইব্রেরি বা সেন্ট্রাল লাইব্রেরি কি খোলা আছে? আপনার কি কোনো আইডিয়া আছে?
লাইব্রেরি খোলা আছে।
মানে গিয়ে পড়তে মানে রিডিং করতে পারবো কি ওখানে গিয়ে?
এখন সবকিছু অ্যাক্টিভিটি নর্মাল হয়ে যাওয়ার কথা, এক্সেপ্ট আই ডোন্ট নো ফর মানে whether it is limited, reading is limited for limited years or it is open for all years, I don't know.
ও আচ্ছা।
মানে এখনো পর্যন্ত ডাইরেকশন গুলো খুব ক্লিয়ার নয় আমার কাছে আর কি। সেটা একটু জেনে বলতে পারি।
আমাকেও জানতে হবে, মানে আমারও জানা নেই, তাই জন্য।
আমাকে আরেকজনও প্রশ্ন করেছিল, আমি ভুলে গেছি আর কি যেটা জানতে। লাইব্রেরি ফেসিলিটি মানে রিডিং এটা যদি এখন অল ইয়ারের জন্য এটা ওপেন নাকি কিছু কিছু ইয়ারের জন্য এটা ওপেন সেটা আমি জানি না। The problem is that when everybody comes, there is not a problem. But what you see is the tendency is that people get clustered together. And we all have to remember that at your home, your parents are there. And you may be more stubborn and resistive towards any attack, viral attack or anything. But you may be a carrier of these things back to your home. So we all have to be careful about that thing. We may carry it to our home, we may carry it to other persons when we are moving from your place of residence to university and back. You are going by some transportation. And there not only you may carry it back to your parents, you may also carry it to your co-passenger. And we all have a responsibility to be somewhat restrictive in our movement. We cannot be like we have done when there is no such thing. We have to think about this thing, all of us. We have all a social responsibility. এগুলো বুঝতে হবে, নিজেরটা বুঝলে হবে না।
হ্যাঁ স্যার।
আমি 1 মিনিট চুপ করে বসে থেকে আবার আরম্ভ করবো, বুঝেছো? জাস্ট 1-2 মিনিট কথা না বলে বসে থাকি।
ঠিক আছে স্যার, অসুবিধা নেই কোনো।
Now, let me start, because it is becoming difficult also to sit. Now, in the flow field given by along the x direction, y direction, and z direction, we take a two-dimensional control volume because we are considering that the flow is two-dimensional in nature. And along the third dimension, things are uniform, it doesn't change. So what we can do is that we can take a unit depth. The depth of this control volume, we can take it as a control volume of delta x, and the length along z is 1 unit, because nothing is changing, so we don't have to consider anything along z. Only thing, because it is a volume, so it has to have a depth also, and also something is entering through an area. You have to consider some area given by delta y into 1, and if you take an area along this thing, it will be delta x multiplied by 1. So we take a two-dimensional control volume with a depth equal to 1, and the dimension of this control volume is given by delta x along x and delta y along y, and this corner may be situated at a distance of x comma y. Okay, and what z doesn't matter, because at each and every z it is the same. So we take this point as if it is at having a coordinate of x comma y and any z, and this coordinate is x plus delta x comma y, like that. Xy, it is x comma y plus delta y, like that. It is x plus delta x, y plus delta y. Now, through this phase, the mass that is entering is given by rho into v. Rho into v is what? Any idea? Okay, we'll come across that thing. The volume that is entering through this phase is given by the velocity component normal to this phase, that is V, and the area is given by delta x into 1. So the volume that is entering, the rate of volume that is entering is given by velocity into area. Velocity into area gives you meter cube per second type of thing. Velocity has a unit of meter per second, area has a unit of meter square. So if you have velocity into area, you get the meter cube per second. There is a volumetric flow rate, and that if you multiply by the density, you get the mass flow rate that is entering into this control volume through this phase, bottom phase, having a length of delta x and a depth of 1. So the area of this bottom face is delta x into 1. And through that, the volume rate of flow that is happening is the velocity component perpendicular to that face, that is V, multiplied by the area delta x into 1. So that is the rate of velocity inflow into this volume multiplied by the density. It gives you the rate of mass inflow into this volume. And through the top phase, the certain rate of volume is coming out, along with that certain rate of density mass is coming out, and the volume is given by, it is similar to this. Here it is V, here it will be V plus del y into delta y, del y of V into delta y. Now here what has been done to begin with is that it is taken that density is also changing along x and y. Okay, so when we are deriving this equation, we consider that density is also not constant. So not only u is changing with x and y, v is changing with x and y, density is also changing with x and y. So what is the density over density into velocity? Here was the rho v. Here it is rho v plus del y of rho v into delta y. By applying the what you call Taylor series type of thing, if the value of rho v here is rho into v, here it is rho v plus del y of rho v into delta y. The rate of change of rho v within this small distance and multiplied by the delta y gives you the total change of rho v within this distance of y to y plus delta y. So whatever the rho v value, that is now changing to rho v plus del y of rho v into delta y, and that multiplied by the area is delta x into 1. So that is a mass flow rate coming out of this thing. Again, let me repeat, is not only whatever the mass is entering and mass is leaving, they are not dependent only on V change, but also depends on the density also may change. There may be certain cases where density also may change. So it is a case where both x, y, along x and y, u and v both are changing, and also density is changing. Or finally, we'll take the case where density is constant. Now, similar to that, the mass that is entering through this phase is given by, in a similar way, rho u into this area is delta y into 1. The depth is 1. So the area is given by delta y into 1. The mass rate of flow into this control volume, the mass rate of outflow out of this control volume along x direction is given by, along this phase is given by, here it is rho u, here it is rho u plus del x of rho u. ওটা অন করতে ভুলে গেছি।
Recording.
The rate of mass outflow from this space is rho u plus del x. This is delta x. Del x of rho u into delta x whole into area is delta y into 1. So these are the mass inflow outflow quantities, and because of this mismatch in mass inflow outflow, there may be an accumulation of what we call mass, and the mass at any instant of time is given by rho into delta x into delta y into 1. Okay, delta x into delta y, delta x delta y into 1 is the volume of this control volume, but multiplied by the density, get the mass within this control volume. So we can now write down the mass conservation equation given by the rate of change of mass within the control volume, del T of rho, this mass within the control volume is rho into delta x into delta y with the depth equal to 1. We are not writing that thing. So rate of change of mass within the control volume, that is equal to the inflow of mass given by rho u delta y. Rho u delta y plus rho v delta x inflow minus the outflow, that is given by these two quantities. So the net rate of inflow is what is causing the rate of change of density within the control volume. The rate of change of density mass within the control volume is equal to the net inflow of mass within the control volume, not density. Rate of change of mass within the control volume is equal to the net influx within the control volume. Now, if we divide both sides by the volume of this control volume, that is delta x delta y into 1, because they are constant, we consider a constant control volume, shape and size of the control volume. So we can take it out of this, delta x delta y comes out, it remains del T of rho plus